Okay, so the last speaker this morning is Frank Smith from UCL, and you'll talk about melting of wall-mounted ice in flowing water.
Okay, thank you very much. This mathematical modelling is on melting of ice in flowing water with various collaborators as shown there. What we'd really like to do, motivated by the aero-icing application, is understand how an ice particle gets through a layer of water on an aerofoil surface and then hits the surface. It may then shatter or may bounce or stick, we don't know. But melting is involved in this process as well, and this is an aspiration. We don't understand much about that yet. So instead of doing that, let's do something that we can understand, hopefully, and that's having an ice lump or step up on the airfoil surface, a solid surface. So in this setup, there's shear flow going on of the air above a water layer, as on an aerofoil, and a warm wall, and then a cold patch of wall on which the ice is sitting. And we're going to try to predict the shape of the ice, the interface, as time goes on. This will mostly be for melting, but in principle it could go on to the freezing application. In most applications here, the time scale is often relatively large, so we'll take advantage of that. So start with the Navier-Stokes and thermal equations as shown here, involving a Reynolds number, non-dimensional form Reynolds number, and sigma is the Prandtl number. The Reynolds number is typically large. The boundary conditions on the ice surface, unknown surface y equals f star, are shown here. So a no slip condition on the u and the v, with involving the density ratio r star of water to ice. And then there's also a temperature condition that you must hit the melting temperature. That's been normalized or non-dimensionalized to -1. And then a Stefan condition involving d theta dy, which we'll show in a minute. So that's on the ice, and elsewhere on the airfoil surface, we have the constraints of no slip and a prescribed temperature. Let's take it, keep it easy, as easy as possible first of all. R star we mentioned already. The wall temperature we'll think of as being continuous with the temperature underneath the ice. We're assuming the ice is all at melt temperature, again as a sort of starting problem. That's all at -1 temperature. And yep, the parameters involved are Reynolds number, Froude number, and Weber number, and they're all large globally. So we're going to neglect surface tension and gravity and work with the Reynolds number as defining the typical viscous size of the water layer. Sigma, the Prandtl number, is we're going to take to be order 1. It's around 6 to 8, 6 to 9 in these applications. The Stefan number varies over a fairly wide range, but is not too excessive. So we'll be thinking of that as order 1 as well. Yes, so the scenario of interest we're aiming at then is going to be involving the Reynolds number being taken as a large parameter, and we're working locally close to the surface where the oncoming shear flow is a uniform shear, so U equals Y, and also the temperature profile is whatever it is at the wall, and then can vary linearly, grow linearly, or decay linearly as Y gets larger. The ice hump is shown here, so it's a cold wall there, warm wall here, and we've done a local scaling of velocity. So the length scales in X and Y have been compressed, and that's it. So in this region we get the nonlinear boundary layer equations holding, as shown here, full continuity, streamlined momentum, and thermal equation. The du dt is absent because we're working on a slow time scale. The pressure, as usual in a thin layer, is independent of y, the normal. And that's it. So that's using a thin layer approximation throughout. Why focus on this scale? Well, the nice thing about this, we think, is that we've captured the viscous and diffusive effects together. Also, and it's in one single layer. There are no sub-layers involved at all. So this seems a reasonable starting problem. The boundary conditions involve the background shear and heat transfer. So there's the U going like y, or lambda y, far up or far upstream. The temperature is like phi y at up there or upstream. That phi can be positive or negative, so there's warmer water or colder water up above in this model. And then the wall conditions are, yeah, we've seen it already, no slip and prescribed temperature. But on the ice itself, the temperature's got to be -1, and y equals f is unknown. And then here's the Stefan condition, which is df dt is proportional to the temperature gradient, unknown temperature gradient on the ice. Okay, so as a first step in that nonlinear problem, let's linearize it, look for small disturbances where the height of the ice is small, order h, yeah, and substitute in velocity, horizontal velocity u is lambda y plus something small, v and p are small, and the temperature is theta, which is order 1 to the order, because it's governed by a linear equation anyway. So substituting in, then we're going to get full continuity. Instead of u du dx here, we're getting lambda y du dx. And so on, that's the same. And similarly, instead of u d theta dx, we're getting lambda y d theta dx. And there's the Prandtl number. Subject to conditions which are, as we've seen before, the change is that the ice shape now appears as a condition on the u velocity. That's been Taylor expanded or linearized down, and there's the Stefan condition again. Okay, so that's the system now. It's a linear PDE system essentially in x and y, but with time evolution in the background. This equation now can be solved by a Fourier transform in x. So we get lambda y I alpha theta on the left-hand side, where alpha is a transformed variable, is equal to theta y. That's the area equation for the transform of theta. Okay, so here it is written down that the theta, apart from phi y, theta is a multiple of the area function of I alpha, etc. And the multiple there is the temperature at the wall. That's the function c transformed. So that gives us the temperature profile, and then we can, from that we can deduce the derivative of the temperature at the wall, and that's going to tell us how f is going to vary with time. This function d turns out to be like this. It's the derivative of that guy, and it's converting back to real space. It gives us a convolution integral involving the temperature at the ice, that's C of S, integrated by this x to the minus 1/3 viscous response, and that's it. And then luckily this d term that appears on the right of the equation is independent of time, so it's very easy to integrate this up to get that f is the initial shape plus d times the scale time, as shown here. Okay, so let's look at some examples of what this gives. We'll try to determine the ice shape and also the time it takes to melt. So the first case here is with an ice step. It's a sort of exponential step, 1 minus e to the minus x or something, times 0, and then we let the system run. And increasing time, you see the leading edge moves to the right, the contact point at the front of the hump, front of the step moves to the right, and and there we are. The contact point's determined by demanding that F equation gives F being positive. If it gives F 0 or negative, then then melting has taken place at that X value, and so we would simply put F is 0. So it's very, very simple stuff. Here phi equals 1, that means the water upstairs is warmer, and that has the effect of increasing the melting, accelerating the melting, and so we get to this same effect as before, but it's occurring much faster. If we make phi equal to -1, so we've got cold water on top, that's going to delay the melting. In fact, it produces freezing on top of the step as shown here, but still the melting takes place at the front, so the contact point moves to the right as shown here, but very slowly. If you make it even colder up top, so phi is -2, then that process at the leading edge is reversed, and you get ice growth at the leading edge. Now that ice cannot grow along the wall upstream because the wall is higher temperature. So what we're left with then is a step, a forward-facing step building up at the leading edge. Formally. What happens really is that the model is failing at this stage because in this modelling we have to assume that the functions are fairly smooth and the derivatives are not too extreme. Here we've got a forward-facing step building up. The model is going to fail just upstream of that. So what we imagine is that there must be some extra effect coming in here, which will produce upstream influence, and presumably an eddy will form, a separation eddy will form, and perhaps produce a stagnation point just at some height here. And that's a candidate for producing a horn or a prong of ice poking to the left upstream. Still, that's speculation. We don't know. So it's all about jeepers. Yeah, humps. It's a similar process. The contact point in all these cases moves to the right. The trailing edge point, the other contact point, moves to the left, and eventually complete melting takes place, no matter what the size of H that we have here is. This is now using the numerical solution of the boundary layer equations. The red lines there show comparison with the linear theory, just to check. Here's the details of one case in particular. So the initial shape was taken as a parabola, and you can see that the melting is completed by a time of about 0.2 here, and the final shape is always a little parabola of ice which disappears. And here's showing the contact points, x leading edge, x trailing edge, against time, and again they come together at a time of about 0.2, scale time 0.2. The pressure correspondingly and the wall shear evolve as shown here. As the ice melts, all these variations tend to 0. For higher ice humps, so now we're thinking of the ice being so large it's poking out of the viscous or diffusive layer. Numerically, you find that we see the onset of flow separation over the leeward side of the ice. Which way did I go? Oh God. Sorry. And also the negative heat transfer is showing pronounced variation at these higher heights before settling down as melting takes place. I cannot work out this machine. So here's the evolution of shapes for steps. It's shown here for 8 for height 0.6 and that's these curves, and then 0.4. As the height increases, the melting takes place much more slowly. Surface shear evolves here. So this is a fairly steep hump of ice at first, step of ice, and we see the surface shear at the front of the ice is large as the water flow hits the front face, and then there's a decrease, but the flow does never separate. And then as time goes on, this surface shear settles down with melting taking place. The negative heat transfer is shown here. At time 0, it's this very strong effect, but then as time goes on, that diminishes. The mathematics of what's going on for large H here is a strongly nonlinear effect as the ice pokes out of the viscous layer. You might expect there'd be a mainly inviscid response as you go out of the viscous layer, and that seems to tie in. So F is now scaled with H like that, but H is large, and on a large scale, Y is H times something, we get an inviscid solution as shown here. The pressure comes out as being minus F squared, roughly speaking, and the temperature profile can also be worked out to be some fancy square root. We then have to reconcile that with the no-slip conditions on the ice surface. So there's a viscous sublayer of order h to minus a half thickness, and that gives us retrieves the full boundary layer equations as shown here. UUX plus VUY, that's minus dP dx, which is prescribed as minus F squared, gives f of x, and then the temperature equation linked with those is again in full. The difference is that the pressure gradient now is prescribed, so we're dealing with a classical situation, and the boundary conditions are classical as well. U tends to lambda f at the top, that's the sort of slip velocity driving this thin layer, and there's no slip on the ice surface, and there's the Stefan condition, df dt is minus d theta dy. You'll notice the ice surface has been written as y equals naught. The nice thing about the boundary layer equations is that you're able to, if you work in terms of y minus f instead of y, this is the parameter transposition, then you can always put the unknown surface at y equals 0, and the f appears in the upper boundary conditions. Yeah, so that's it. This is a problem that we have no solution yet. It would be nice to get onto that eventually. It's coupling the flow with the ice and temperature evolution. Just wonder what happens. I'd like to go back to the linearized solution now for some more recent work. First of all, the effect of an undercooled wall. So far we've had the temperature being -1. Supposing it's colder than that, let's call it K, which is below -1. Then the equation for the Stefan relationship gives us df dt is equal to some multiple of 1 over f minus bx minus a third. Bx minus 1/3 is the viscous effect we've seen before. The new effect is in this undercooled wall. And here's a typical solution. So we start with a parabola of ice and then just run this very simple ODE. And at time 0.2, it's the shape has gone to this, 0.4 is just there, and then there's a steady state limit which is reached. The ice never completely melts, and it's given by simply the right-hand side equals 0. Again, there's another effect in the linearized solution which we've seen a bit of, is the effect of negative phi. That's the heat transfer up top. And if we start with zero heat transfer, we get the blue curve here, which is what we saw before. The ice melts at a scale time of about 0.2, And then let's now make phi more and more negative, colder and colder water up there. And go from the yellow to the green, and then somewhere between the green and the red stage, so somewhere between phi is minus 0.5 and minus 1, the ice does not melt completely. So the leading edge keeps moving downstream, but eventually the trailing edge moves downstream as well at a rate which is more or less the same as the leading edge. So you get this hump of ice, the flow's coming that away, and this hump of ice is gradually moving along the wall according to the model. Okay, I'll finish off with other phase change situations of interest. Okay, supposing instead of underwall cooling, you've got underwall heating. What happens then? So now we've got a warm wall upstream as before, but we're warming underneath the ice. This is of some engineering interest because that's a way to try and shed ice off a surface. So I've got no solutions for this, but it seems fairly obvious the ice is going to take off. This warm wall underneath the ice will melt the ice initially in a thin layer just above the wall, and at that stage the oncoming water is going to try to infiltrate into that thin region, and eventually that ice is going to be shed. What happens if the wall is, say, warm and then cold, is much more tricky. If we have cold wall and cold wall, then growth can occur leftwards. So this step of ice could move to the left along the wall. That's okay. If the ice does melt at the wall, then we've got this situation occurring. So warm water, warmed wall, and that ice which has just been shed is presumably going to travel downstream, and it could stay in the water layer or go down and hit the wall again, or it could fly out of it. We don't know. Also, the ice is going to melt, presumably, so it's going to change shape and orientation, and these are interesting problems. So that's lift off after impact. Before impact, this is the original problem I posed at the start, but there's a challenge of trying to predict how the ice gets through that water layer, if it's going to melt in warm water. So changing shape, and the ice may melt completely before it hits the wall, or it may just hit the wall. Who knows? Various other things have been going on, which I'll just mention. This is the 3D extension done by PhD student T.D. Dang, and she's managed to make sense of the 3D version of the on-wall ice problem. And these are her results for a melting case, a sort of parabola or paraboloid initially, and then it's melting at a time of about 1. The final recent extension I'd like to mention is with a student called Reza Batley. He's looking for a PhD place somewhere. He's very good at computation. But this is for a blocked channel, trying to predict how long it takes to unblock a channel with ice in it. So that's a sort of starting flow, beautiful eddies downstream of the ice. And this is what's predicted. This is from solving the boundary layer equations again, but from wall to wall, and using a Prandtl-like transposition to handle the unknown shape of ice. And there it goes. So a prescribed temperature profile is input. Warm temperature is input here, something like a parabolic profile. and also parabolic profile of the velocity. And the ice is at temperature -1, and the water locally is blue, temperature -1. And then you can see as time goes on, the warm effect gradually comes along, and the ice starts to melt. The blue is pushed away, close to the surface of the ice, and the ice continues melting, and it's all over in a scale time of 0.1. So at this stage, the flow and temperatures are in their steady states. Okay, for that sort of case, here's a plot of the contact points as they vary with time. The yellow curve we've seen before. It's from the analysis, and that assumes that the length of the ice is small compared with that channel effect. The red and the blue are from the computations for a fairly small initial hump of ice, and well, it's great to see them get them in the right same ballpark. The agreement's not perfect. The time to complete melting is about the same, but that value there. There is this slight off peak in the numerical results. We think that's due to the length of the initial ice being 0.2 compared with the channel width 1, say. The analysis only applies if that's an asymptotically small number. So 0.2 is, in this case, isn't smaller. But also the ice, the viscous thickness about the ice scales like length to the 1/3. So that's 0.2 to the 1/3. So and that's meant to be asymptotically small for the analysis. And 0.2 to 1/3 gets you sort of, I don't know, 0.6, 0.7. And that's definitely not small enough, not asymptotically small. So that, anyway, that's our excuse for these two curves not being very, very close. Okay, so I'll finish there just with the conclusions to say we've done something which you think is rational about wall-mounted ice and flowing water. We can't do much yet about freezing of such ice. It's difficult to model pre-impact melting or freezing, and also post-impact lift-off due to heating and all these other interesting effects we'd like to study. Some of this is going to be studied by Jacob Jepson, who's just joined as a 3-year postdoc at UCL, and so I wish him good luck. Okay, I'll finish there. Thank you.
Any questions?
Somehow your situation is not that far from the dendrite that grows in a liquid. Mm. And my question is, you may have a difficulty for the boundary condition at the tip of your ice, no? In terms of temperature and gradient of temperature, don't you have any discontinuity of the gradient or something?
Well, in this, I must admit, I worried about that at first. I think it's to do the scaling. On that scale, it's a very simple matter. Is F positive, or F has got to be positive or 0, and that seems to settle.
Because for us, that was one of the difficulties. So we imagine there might be some boundary layer there. So you can solve the correct temperature condition at this point. Or?
Yeah, I think so. Yeah, everything is very, very shallow.
You have a discontinuity of the temperature between the cold and the warm wall, or the opposite way. No? You have a warm wall on one side, a cold one on the other one.
Yes, we had warm and then cold and then warm. I think in most cases, yeah.
Thanks, nice talk. So back in the 90s, Higuera did a paper with freezing of a step in a viscous boundary looking at separation. I was wondering, so did you see separation when you looked at your freezing model in here? So they saw some situations where you got a triple deck style structure near the front of their ice step, and I'm wondering if you saw that as well.
Yeah, we've certainly got cases with flow separation downstream on the leeward side. The flow's coming this way, there's the hump, and then you get a separation there. I can see separation occurring upstream if freezing takes place. The ice grows, and so you get an upstream eddy. Does this? But there's no triple deckery here.
There's no triple deckery in this. Okay.
Yeah.
Okay. I'll talk
Just
to you
a
after.
single layer. Yeah. It may be that this is a subset of what Higuera did. Yeah.
Any other questions?
Yes, I thought that was a triple deck viscous and viscid interaction theory that you use when
No,
when the obstacle is too high, is too large, is too.
This is a much smaller scale.
So still you're in a kind of a linear interaction. It's a very thin obstacle.
Yes,
Very short obstacle.
Thin yeah, short, shorter than
But
that.
then how did you capture boundary layer separation?
Oh, that's within it's a non-linear viscous layer. So the boundary layer is, say, that big, and we're working in the viscous layer, and we can get little separations. Yeah. Good.
Just wondering, in the numerical results you showed just a couple of slides ago, you
Yeah.
had warm fluid coming from one side, but it seemed like the ice was melting symmetrically.
Yes.
It's not expected, because you have warm water coming on one side. I would expect it to be asymmetric from the left, no?
See if I can get it back.
Here.
You mean that one? Yeah, Reza ran his code from Y0 to 1, so he ran it to allow for asymmetry. But the initial state is symmetric, and the solutions that came out came out symmetrically. Okay, I guess if he'd put in a temperature profile which was non-symmetric, then that would have made it non-symmetric. Yeah.
More questions? And then let's thank Frank again.